Hello, I'm posting 4.2 day 2 again, video 1. That'll focus on the first goal. Distinguish different approaches to probability questions based on keywords all, at least, exactly. Video 2, which was visible yesterday, addresses goal number 2, determine the probability of sums. Okay, so that's example 3. All right, so yesterday was Tuesday, May 5th. Happy birthday to those of you that had a birthday yesterday. Okay, so note number 1, the theoretical probability is also referred to the classical definition of probability. They both find the probability of event A, so that's our desired event or a desired outcome, using the formula probability of event A is equal to the number of times you can achieve your desired outcome divided by the number of outcomes in your sample. Okay, so the probability of event A is the probability of your desired outcome happening. The number of desired outcomes, right? Number of times that outcome A has occurred is also called the event space. So in other words, if you're looking forward to something that's desired, right, you can call that an event, right? So if you're wanting your chocolate chip cookie, okay, the event is all the times that you can get your chocolate chip cookie. So if there's the 5 chocolate chip cookies in a jar of 20 cookies, your event space includes all of your 5 chocolate chip cookies. N of S is the number of all possible outcomes. So all the possible outcomes in our cookie jar would be 20 because that includes the 5 chocolate chip cookies plus the other 15 that are different types of cookies that we don't desire, okay? It's also called the sample space, all right? So example 1, each letter that spell Win at South are written on separate pieces of paper of equal size. The letters are put into a hat and that hat is shaken. So I guess I've changed this to hat. Determine the probability that a T is selected. Okay, so if our probability, so that's our desired outcome. Okay, so the probability of getting a T is equal to the number of T's, okay, divided by the number of total letters. Okay, so that's equal to number of T's. So there's 1 T there, there's another T there, so in total there's 2 T's divided by the number of total letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10. It's a fraction, reduce it, equals 1 out of 5. Okay, so that's our answer. So the probability of getting a T is 2 out of 10 or 1 out of 5. Determine the probability that an N is selected. So the probability, so N is selected, that's our desired outcome. Okay, so probability is a fraction. Okay, that's why you have to have your probability of your desired outcome, which is your probability of getting an N, okay, is equal to how many N's are there? Okay, so it's the number of letter N's, okay, divided by the number of total letters. So how many N's are in the phrase Win at South? There's just this one. So there's 1 N out of, we said that there were 10 letters. That's not reducible. Probability is in a fraction form. Okay, so if you have probability, you have to write it as part out of a total. Okay, so probability is in a fraction. 4 coins are tossed in the air at the same time. Find the probability that this happens. Okay, so again, probability, so this is our desired outcome. So 4 coins are tails, so the probability of 4 tails is always equal to getting what we want. So that's the number of outcomes that give us 4 tails divided by the number of total outcomes. Okay, so how many outcomes will provide us with 4 tails? Well, we could get a tail on coin 1, a tail on coin 2, a tail on coin 3, and a tail on coin 4. So this is coin 1, this is coin 2, this is coin 3, and this is coin 4. Well, there's only one trial that can do that, right? That's one trial. So the number of outcomes that give us the 4 tail is how many trials will give us what we want. Well, there's only one trial. There's only one way of doing that, okay? So there's one outcome that will satisfy us. Now, the number of total outcomes is equal to figuring out how many outcomes are possible with each coin. Well, in coin number 1, there are 2 outcomes, head or tails, and you multiply that to the number of outcomes on coin 2. Well, there's only a head or a tail possible, so that's 2. So the total number of outcomes on coin 1 times the total number of outcomes on coin 2. Well, coin 3 has the same number of outcomes as coin 2 and 1, and coin 4 has the same number of outcomes on coin 4. There are 2 outcomes. So we want all the possible outcomes, okay? So a tail or a head, there's 2 outcomes for each and every coin. So in total, 2 times 2 is 4, times 2 is 8, times 2 is 16. So the number of total outcomes is 16. Right? Find the probability that at least one is heads. Okay, so that's our desired outcome. How many ways can we be satisfied, right? So the probability of at least one is heads. Well, that's equal to the number of outcomes that are at least one head divided by the number of total outcomes. This here, outcomes, not outcoins. Okay, so this total is going to remain 16 because this intro is applied to A and B and C. Okay, so we still know that that's 16 possible. So if I want at least one head, I could be satisfied with getting one head out of 4 coins, or I could be satisfied with getting 2 heads on the 4 coins, or I could be satisfied with 3 heads on 4 coins, or I could be satisfied with 4 heads on the 4 coins. So if I get one head, what does that look like? Well, coin 1 could be a head with the other 3 coin tosses being tails, or I could, instead of getting it on the first coin flip, I could get it on the second coin flip, and the other being tails. Or I could get the head on the third coin flip. and the other being tails. Or I could get the coin toss coming up heads on the fourth coin. So each of these represent coin 1, coin 2, coin 3, coin 4. So in each of these scenarios, or you can call them trials, in each of these trials, I'm still satisfied because I've got that one coin turning up head. Well, there's 4 in total. Okay, so there's 4 in total. But because I have this option of at least 1 heads, I could look at the scenario or the number of trials that give me 2 heads. So 2 heads. I could get the first 2 coins turning up heads, where the other coin 3 and 4 are tails. I could do it then where 1 is tail and then the coin 2 and 3 are heads, coin 4 is tails. Or I could do a coin toss where I get a tail, a head, and a head. Or I could get a tail, a head. Oops. So I'd need to add this. So I have to be thinking of possible combinations, right? So I get 2 in the first place, or I get 2 in place coin 2 and 3, or I get what I want in coin 3 and 4, or I get what I want in coin 4 and 1. Now, the other options are a head followed by a coin toss that's a tail, head, tail. Okay, that's another possibility. Or I can do a tail, a head, a tail, or a head. Now these ones aren't as obvious, I don't think. They're not as obvious. So I get the number of trials to give me 2 heads, 1, 2, 3, 4, 5, 6. So I get 6 there. Okay, so what else am I going to have as my outcomes? So I can get 3 heads. When will I be satisfied with that? Well, in trial 1, I could get coin 1, coin 2, and coin 3 all in a row getting a heads. Then the coin 4 is a tails. Or instead of the tails coming at the end, it could come as the third coin toss. So head, head, tail, head. Or I could get a tail on the second coin toss with all the others being a head. Or I could get a coin toss where tails comes up first and then all 3. So you're really having to think logically about the different trials and what each trial could produce if this was my desired outcome. So these are all my desired outcomes, right? So I've got 1, 2, 3, 4. I've got 4. So see how I'm increasing the number of outcomes that will satisfy my desired outcome, which is at least 1 is heads. So then scenario here, this 4 heads is one of my outcomes, is at least 1 heads. Well, I've got 4. So how will that happen? Well, 4 coins all turning up heads. That's the only way I'm satisfied. So that's 1. Okay, so I've got 4 plus 6 plus 4 plus 1. 4 plus 6 plus 4 plus 1 all over 16. So that gives me 10 plus 4 is 14 plus 1 is 15 out of 16. Now if I wanted to, I could have done it this way, where I say the probability of getting at least 1 head is the probability of no heads. It's the reverse, right? So because getting at least 1 head, I've already said, is getting 1 head, or getting 2, or getting 3, or getting 4. The reverse, or the opposite of that, is the complement, right? So the only option that's not included is getting no heads. So I could go 1 minus the probability of no heads. Well, what is that? That's the same as the probability of all tails. Well, we've already got the probability of all tails. So 1 minus 1 over 16 is 15 over 16. So I could have done this answer like this. The other way of doing it is a tree diagram. And if you study this long enough, you'll see that I would have to count up the number of branches that included all the possible ways that I could get at least one head. Okay, so this is very time consuming, and it's also very complicated because we have 16 total outcomes. Okay, so we're going to talk about this down the road, but this is a third way of getting the answer to B. All right, so we're going to talk about tree diagrams down the road. But this is one that you might be interested in doing. Okay, so anyway, so there were three ways of doing this question. All right, so what about if you get exactly 3 tails? So that's your desired outcome. So the probability of getting 3 tails is equal to the number of outcomes that give us 3 tails, all divided by the number of total outcomes. Okay, so if I'm only interested in 3 tails, this is my work over here, 3 tails, I could get a tail on coin 1, coin 2, coin 3, where coin 4 is the head, or I could get a tail on coin 1, coin 2, not on coin 3, but on coin 4. I could get a tail on coin 1, not on coin 2, a tail on coin 3 and coin 4, or I could get no tail on coin 1, but a tail on coin 2, coin 3, and coin 4. So in total, 1, 2, 3, 4. It's 4. So I have 4 possible outcomes that will satisfy my desired outcome out of 16 total outcomes, which we said over here. Notice that 16 continues to be the denominator. Okay, I have to reduce like I normally do as every fraction gets reduced. So it becomes 1 out of 4. Okay, this answer is also possible by using this tree diagram. So the tree diagram, because it visually gives you all the possible scenarios, once you draw your tree diagram and you give yourself enough space, you could actually use your tree diagram to answer all of these scenarios. But again, I didn't break this down and spend time doing it. We're going to do it down the road in a couple of other lessons down the road. But again, the tree diagram could have been useful as well. I'll stop there because video 2 from yesterday was visible and it confirmed how to do example 3.